All right, let's get to it and meet our contenders. In one corner, we have physical vapor deposition, PVD, and in the other, we have chemical vapor deposition, or CVD. Now, both of these methods are designed to lay down a super thin layer of material, but, and this is the key, they go about it in completely different ways.
So, first up is PVD. The easiest way to think about this is like atomic spray painting. Seriously, you take a solid block of your coating material, you zap it inside a vacuum chamber so it vaporizes into individual atoms, and then those atoms fly across and condense onto the part you want to coat. It's a physical process, plain and simple.
And its counterpart is CVD. Now, this one's a whole different ballgame. Instead of vaporizing a solid, you pump special gases into a chamber. And right at the surface of the part, those gases react with each other. And, like magic, they form a brand new solid material that grows right onto it. So it's less like spray painting and more like baking a part in a chemical fog that creates this perfect, even crust all over.
So you can already see we've got two very different ways of doing things. Let's break down what that really means in practice, starting with the fundamental mechanics of each process. Okay, so this is the absolute crucial point. With PVD, the material you start with is the same material you end up with as a coating. It just changes state from a solid to a gas and back to a solid. But with CVD, the coating is a completely new material that's formed by a chemical reaction. And that single difference, it's the key to everything else we're about to talk about. Now check out the temperature difference here. PVD is a pretty cool process, relatively speaking. It often runs at temperatures your oven at home can reach. This makes it perfect for coating things that can't handle intense heat, like certain plastics or tricky metal alloys. CVD, though, it is a high-temperature process, often running way above 900 degrees Celsius. That crazy heat is what kicks off the chemical reaction, but it also means it's only for materials that can, take the heat.
So let's see how this leads to one of the biggest, most important, practical differences between the two. How well they can actually cover a complex part. This is where our whole spray paint versus chemical fog analogy really comes to life.
PVD is what we call a line-of-sight process, and it's exactly what it sounds like. The vaporized atoms travel in a perfectly straight line from the source to the part, just like paint shooting out of a spray can. And you guessed it, just like spray painting, that creates a problem. PVD can only coat the surfaces it can see. So if your part has any complex internal channels or deep grooves or hidden surfaces, well, those areas are going to be in a shadow, and they just won't get coated properly, if at all. But CVD, it's what we call conformal, and that's because the coating is formed from a gas that fills up the entire chamber. That gas, it gets everywhere. And this right here is CVD's biggest advantage. That chemical fog just envelops the entire part, inside and out. It flows into every single nook and cranny, and it guarantees a perfectly uniform coating, even on the most ridiculously complex shapes. This is exactly why it's so vital for things like intricate valves or coating the inside of a pump cylinder. Okay, so we know how they work and how well they cover a surface. But the real question is, how do these coatings actually perform when the pressure is on? Let's put their durability and the resistance to the ultimate test. When it really comes down to it, standing up to extreme wear, abrasion, nasty chemicals, which one actually comes out on top? Let's take a look at the data. This table really tells the whole story. First, just look at the thickness. PVD coatings are incredibly thin, less than 5 microns. CVD coatings, on the other hand, can be 10, 15 times thicker. And that thickness directly impacts performance. PVD gives you moderate wear resistance, sure, but CVD's thickness makes it a beast for heavy-duty abrasion. And for corrosion, that same thickness gives CVD this fortress-like pore-free barrier, while the thinness of PVD can sometimes have tiny, microscopic pinholes. The difference is just stark. When you look at it like this, across the board, in thickness, in wear resistance, and in corrosion resistance, the performance of a typical CVD coating is just in another league. It's simply a thicker, denser, and far more robust shield. So after all that, how in the world do you actually choose between them? Well, it's not really about which one is better overall. It's about which one is the perfect tool for a specific job. You'd go with PVD for its unique strengths. That low processing temperature makes it the only choice for heat-sensitive materials. Its incredible thinness is perfect for things like precision cutting tools, where you can't change the dimensions at all. And of course, you see it everywhere in decorative finishes, on watches, faucets, you name it, where it looks great and is also really cost-effective.
But you turn to CVD when failure is simply not an option. For those heavy-duty parts in oil and gas or aerospace that face unimaginable stress. For those super complex parts with internal surfaces that PVD just can't reach. For any environment with aggressive corrosive chemicals. And, of course, in high-tech fields like semiconductors, where the purity and uniformity of a CVD coating are absolutely critical. So, what's the final verdict? It's this. PVD and CVD aren't really competitors. They're more like two highly specialized tools for totally different problems. PVD is the precision scalpel, while CVD is the heavy-duty suit of armor.